Hello, everyone. My name is Christopher Yi Wong. I'm from the University of Sherbrooke in Canada, and the title of my talk is the Sensor Observability Index, Evaluating Sensor Alignment for Task-Based Observability in Robotic Manipulators. The catchphrase I like to use for this paper is, we look, but do we actually see? So the main purpose of sensor observability is to answer this question. Given an articulated robot with distributed axial sensors, how well does the current configuration observe the world? So for example, the robot Baxter has joint torque estimation. Sensor observability could be something like, how well can joint torque sensors on a serial manipulator reconstruct the interaction forces? So you might think, okay, how does this compare to kinematic analysis using the Jacobian, like manipulability? Well, what if a robot has sensors that are not aligned with the joints? Or what are the effective physics on different types of sensors? So these issues cannot be handled by the standard Jacobian or kinematic analysis. So sensor observability is a more generalized analytical method to achieve the above goal. So let's say we're using joint torque sensors to estimate the end effector interaction forces, and we have an external sensor for ground truth. In a nominal configuration, there is no trouble estimating interaction forces, and the two real and estimated force plots match up quite well. In what we call a sensor observability singularity configuration, the robot is actually unable to observe any forces in the x-axis despite the existence of forces in x according to the ground truth sensor. So this issue motivates the need for sensor observability analysis such that we can determine the existence of such sensor blind spots depending on the robot's joint configuration and sensor layout. So how does one implement sensor observability? So here we have a serial arm manipulator, which includes both joint-mounted and link-mounted sensors, and they have their respective sensing axes as hat. For a joint torque sensor using Denevit-Hardenberg notation, the sensor axis would be along the Z rotation axis and then rotated into your desired coordinate frame. So first off, we have the sensor transformation function, which is a physics-based transformation of each individual sensor. And then we analyze the cumulative effect of all sensors together using the sensor observability function gamma, and that gives us the final sensor observability vector S, which is a single vector that tells us how well each task-based axis is observed overall. Finally, we have the sensor observability index O, which converts that cumulative vector S into a scalar index value. So ultimately, the goal of sensor observability is to see how well the sensors align with each task-based axis. So for your ease of understanding, you can think of task space as Cartesian space, but this is not always the case depending on what you're trying to analyze. So sensor transformation function T. So it's a transformation of a single sensor according to the effective physics. So as an example, we're going to look at force sensor transformation with the T sub F, and you'll notice that we have S hat and S tilde. So S tilde is the transformed sensor axes where each element of S tilde indicates which task space axis the ith sensor is observing, and it has linear and rotational components. And this is generated by the transformation of the local sensor axes as hat. So since offset forces generate a moment as well, linear forces can thus be seen by both the linear and rotational force sensing components. So when we're building our physics-based transformation, we include the cross product of the rotational sensing axes and the moment arm on top. And we also use element-wise absolute signs to ensure that sensor axes do not cancel each other out. And since the sensor transformation function is physics dependent, sometimes it might just be the identity for certain sensor types. Now, if we take each individual transformed sensor, we can group them all together and we form the sensor observability matrix, capital S. So now with the sensor observability function, we can determine the cumulative sensing effect of all individual sensors according to a defined metric. So this is all represented in the final vector, final sensing observability vector S, which is the output of gamma, where each element of S represents how well each task-based axis is observed. And if any element of S is 0, then that axis cannot be observed by the sensors on board. So here are some examples of observability functions. First, we have the row-wise sum function, where we just sum up the effect of each sensor. Conversely, we have the row-wise max function, where for each task-based axis, we find the sensor axis that is most aligned with that task-based axis. So these metrics are not perfect, as they have certain flaws, but it's also possible to define more complex ones as well. So as an example, we apply forced sensor observability analysis to one arm of the robot Baxter. So just like kinematic manipulability, we can visualize the final sensor observability vector using an ellipsoid. So we have red for force, blue for torque. So in this random position with full sensor observability, both force and torque ellipsoids are full volume. In these two other cases, there are deficiencies in sensor observability as one axis of the ellipsoid collapses because it is no longer observable. So any force or torque in the observable axis would not be seen by the joint torque sensors. So this is similar to what I showed you at the beginning with the ground truth experiment. So how does sensor observability compare to the traditional Jacobian? So unfortunately, I don't have time to go into any detail, but what we found is that for a serial manipulator with only revolute joints, deriving the geometric velocity analysis and the sensor observability analysis ends up with very similar forms. We can almost think of joint axes as velocity sensors. But despite these similarities, we have two major caveats. First one is that this similarity applies only if joints and sensor axes align in a one-to-one manner, and that the existence of a kinematic singularity does not necessarily imply a sensor observability singularity, and vice versa. In conclusion, I showed you the preliminary formulation of the sensor observability analysis, and it's a useful tool for discovering and avoiding blind spots for robot-mounted sensors on reconfigurable robots. And sensor observability is more flexible than the Jacobian-based analysis. In terms of future work, we're going to formulate it for use with non-fixed base robots and also demonstrate its use in trajectory and posture optimization. So thank you very much for listening, and I will take any questions now.